I'm now very pleased to introduce Dr. Tin Wee Tan, Chief Executive of the National Supercomputing Center, Singapore. Professor Tan is the founding director of the National Supercomputing Center, Singapore, and is an associate professor of the Department of Biochemistry at the National University of Singapore. He is well known in the bioinformatics field, having been a founder in Singapore, BIC in 1996, and in the Asia-Pacific region, AP BioNet, 1998, as well as in the field of advanced internet networking, SingARIN, 1997, and APAN, 1996. As the inventor and founder of multilingual internationalized domain names and a pioneer of the Internet, he was inducted into the inaugural Internet Hall of Fame by the Internet Society in 2012. Today, Dr. Tan will present the Supercomputing Data Center of the Future. Dr. Tan, thank you again for joining us today. Please begin.
And thank the HPC Advisory Council and NCI Australia for giving me this opportunity to speak. Yes, it's right. I'm sitting in my car doing this presentation, but rest assured that I'm not driving at the same time. That would be pretty dangerous. First of all, I like to talk about something that has been bothering me for a long time. And being a biologist, I'm particularly concerned about the environmental issues that surround the incredible usage of electricity by data centers, and in particular, data centers of supercomputers. And it's been bothering me for some time because I've been tasked to build not just the first generation petascale supercomputer in Singapore, but also the next generation one as well. So I've been given this privilege of doing so, and it becomes a weighs heavily on my conscience to realize that there will be up to 20% of the world's electricity being consumed by data centers. And the contribution of the carbon footprint is just going to be incredible. So what can we do? Well, I've been a board director of a listed company, and I'm fully aware that as a data center operator, it's not happening with that community. Being also a user of data centers, running a supercomputer and hosting it in the data center, I'm also realizing that many of my colleagues who are customers of data centers, it's just not happening as well. Other considerations weigh heavily on our minds when we operate a 24/7 system. I now sit in the board of a data center REIT. We go around buying data centers. And I can tell you, the data centers that we buy, we are very worried about the sustainability issues as well. But there are very few data centers that operate at a power utilization efficiency of anything lower than 2 or 1.5. So it's not happening soon in that space as well. So from that perspective, I feel really strongly that we in the supercomputing community, the HPC community, should really sit up and pay attention to how we can lead the way by example. As early as 2015, I was giving a talk at TEDx Singapore, and I was able to articulate some of my dreams back then. And I was explaining to people how the future of data could well be green if we take care of certain important points, especially in the data center space. How do we build and design green data centers, especially to house our energy-guzzling supercomputers? So we have heard about the launch of the incredible Fugaku system, costing in at $1 billion US. And typically, I was informed a few moments ago by the director of this incredible system, housed in Kobe, Japan, that these top data centers typically need 10 to 30, 40 megawatts of power. And you can see from here that it is really, you really need to buy a power station next to it and put one next to it in order to power such supercomputers. And Satoshi Matsuoka told me a few moments ago that had he used typical Xeon Phi systems, he would probably need 100 megawatts of power. Fortunately, he was able to succeed with his ARM system, which is low energy consuming and running at an incredible power efficiency of 16.9 gigaflops per watt. So obviously, one solution is to deal with the problem at the source of the energy consumption. Can we design better chips, more energy efficient systems in order to reduce the amount of energy consumed per flop, per byte of storage, per bit moved over the network? But beyond that, we also need to deal with the issue of cooling. So this is what I'm going to focus on in this particular talk. How do we build a data center housing green machines, but allowing us to increase the efficiency of cooling the system? So one good solution would be find a great place to put a data center. So the Iceland people have been pretty aggressive in doing this, and you would have heard very often that companies, Facebook, Google, Apple, have decided to build their data centers in northerly places where it is pretty cold. And to boot, they also may have been able to tap geothermal energy as well, thereby reducing the entire cost of running the data center in such obscure places. We ourselves in Singapore, 2014, have thought about this problem, and in that period, that many years ago, we thought maybe if we could tap into a data center that far away by using InfiniBand, we might be able to leverage using data centers, housing our supercomputers that we put in those green locations. So we set up doing this InfiniCortex project, hoping to be able to pave the way to tap supercomputing centers that are in suitably cold locations. The other approach then is to look far closely at how do we locate these supercomputing data centers, besides putting in cold places. Singapore is really hot in the tropical area. We can only go so far, and the latency will eventually kill us. So can we find other solutions as well? Well, I'm a biologist by training, as introduced by Brian, and I'm well familiar with nature's symbiosis. What about thinking along the lines of industrial symbiosis, whereby we couple data centers with, say, for example, LNG gasification, where they produce a lot of cold waste? If we can couple these together, using the cold waste as the cooling agent for our hot data centers, and using the hot heat waste that we generate in data centers and to feed it into the energy required to warm our LNG, liquefied natural gas. Now, liquefied natural gas comes in at minus 162 degrees. Now, that's a lot of cooling, cold, and that's a lot of warming that needs to be done in order to bring it up to temperatures which we can feed into greener power stations that will burn that natural gas. Well, it turns out that in 2015, 2016, a company called TerraCool had already had this idea, and they were coupling data center cooling from waste LNG refrigeration system for significant energy savings and environmental benefits. So the question is, well, does Singapore have an LNG facilities? And the answer is yes, and we're building more. And it turns out that Singapore is has an LNG receiving terminal at the Jurong Island, an offshore island outside of main island Singapore. And we've been looking at this possibility. Could we co-locate a data center close to or even within the premises of an LNG plant? Now, people are always afraid that this location will be susceptible to dangerous scenarios like explosions and so on. But the last time an LNG facility exploded was in Cleveland many decades ago. They have certainly cleaned up their act, and the LNG community is very careful in ensuring that the danger levels of this are suitably managed. What else could we think about? Well, can you imagine if every home that requires domestic heat can be matched together with a computer of some kind? Could we embed in the walls processors that provide the compute and yet at the same time provide heat to warm up our homes for domestic use? Well, it turns out that a company called Solar Impulse has already rolled out their prototype QH1 using computer heat to warm homes. They have a high-performance computer server acting as an electric radiator. So if we think in terms of supercomputers, if we take a block of apartments and then fill all the walls up or the corridors up with racks or supercomputers in suitably housed rooms or cabinets, maybe this could be one way in which we could sort of create a mini data center in every home. Could that be a possible urban solution to supercomputing data centers? And what nobody would probably think about doing this, but perhaps we in the supercomputing HPC community might start to ponder about these possibilities. Another way is to ensure that we set good standards for data center availability options. And here you see the Green Grid community has already come up with various techniques to help data center operators really get to grips with the facts. Do you really need to operate your data center at 18 degrees? Could you run it warmer? And what are the cost-benefit analysis? Well, they have built a system that will allow you to do that calculations. And it's essentially buying the mind share of users of data centers to realize that you may not necessarily need to overcool your facility. Could you run at a warmer temperature closer to ambient so that you do not need to waste too much electricity overcooling the data center? They've come up with new metrics, including infrastructure utility effectiveness instead of the PUE, using the IUE to measure the efficiency of your data center, power metrics for IT equipment, as well as data center automation systems. So I got to move on quickly now. Well, what have we in Singapore been doing? Our Aspire 1 system in 2015 was consuming power at 1 megawatt, but we're able to pull it down from 1.37 to 1.08 through several steps. Our 1 petaflop system is actually located in a high-rise data center, 17th floor. I have not come across a data center so high. Maybe the DE Shaw system, 11th story out in America, could give us a run for the money, but at 17th floor, we're pretty high up. So we leverage on this unfortunate situation to really design a data center that will help in the cooling aspect of a 1 petaflop supercomputer. And by avoiding polluting livable areas with heat, we were able to throw out the heat to the atmosphere at level 17 where the winds are pretty strong. We made use of a combination of 3 cooling systems, direct warm water cooling, direct-to-chip warm water cooling. For the rest of the energy, the heat, we use the conventional cryo units, and then we also use chilled water for rear door heat exchangers. Going forward, our warm water dry cooler system that really saved at least 50% of power needed for cooling will lend its way to our next generation data center, which we are in the process of building. That will include digital twin, IoT sensor, AI-assisted systems that will help us drive the PUE even further lower. We were able to use this warm water cooling system in our Aspire 1 facility to allow us to bring the temperature in the room right up to the high 30s and even 40s, because our the cold water inlet is actually at 40 degrees, and it heats the water outlet. The water outlet is actually 45. And the 45-degree temperature of the outlet hot water goes out to the atmosphere, which is running well below 40 degrees. On a really hot day, it might go up to 35, 36. So the temperature differential between 45 and 35, 36 on a hot day can really be sufficient for us to enjoy free air cooling. So our warm water cooling brings out the heat from the chips right straight to the atmosphere. Again, we still are throwing out heat in the atmosphere. Can we further improve ourselves? So one other concept that we explored was intelligent data centers. And the whole idea is to make use of IoT sensors to sense as many aspects of the running of the data center as possible, analyzing outlier analysis of the server nodes, cluster analysis of server nodes, including thermal aware job scheduling, in order to make sure that there are no hotspot aggregation, as well as to map the cooling of the system as closely as possible without overcooling. You can see on the chart on the right side of your screen, without optimization, we just plain cool the whole system without keeping our eyes closed. The shaded area shows how much wastage we are incurring. However, if we can do offline optimization and bring that peak cooling down to the hottest moment in our data center, well, we could cut down on the shaded area. But if we can match that, the amount of heat generated as closely as we can and adjust the cooling accordingly, then maybe we could save even more energy in terms of cooling. So in order to do that, we have to figure out also alternative ways of spreading the heat around. And we have essentially been working on networking the entire city where we could put bits and pieces of supercomputers to serve the needs closer to the community as well as to spread the heat around. Beyond that, we were also thinking about connecting to other supercomputing centers in greener locations with less operational costs. In Singapore, our electricity costs are humongous, 20 plus cents per kilowatt hour, and other locations could be well below 10 cents. So it's a big difference to us in terms of our operational expenditure. So if we can link up to other supercomputers, and in this regard, we thank the NCI for offering us a good deal. The possibility of helping us out if our load gets too much. So I hope that one day perhaps all supercomputing directors and CEOs could gather together and figure out whether we could work together to use high-speed links such as the one drawn in this diagram that are already being built to share our resources, offload peak periods to each other, and really essentially optimize at the level of interoperable supercomputing data centers. So going forward, from October 2019, the government has already announced that they will allocate a significant triple-digit $1 million for NSCC Phase 2. And our supercomputer will now upgrade itself to at least 10 to 20 petaflops systems upgrade for Aspire 2, our advanced supercomputer for petascale innovation, research, and enterprise, which we hope to roll in place by hopefully COVID notwithstanding by 2021. And going forward, we will slowly roll out that master plan. This involves us distributing the heat as well as to engage in several data center optimization strategies, including upping the ante on AI, creating green efficient data center cooling systems, and the smart intelligent operation of data centers using digital twins, IoT sensing, integrated with data center infrastructure management, as well as artificial intelligence techniques to help us not just do preventative maintenance of the system, but also to optimize our data center systems as we go along and to engage in what-if scenarios. So practicing what we preach, we hope that our CFD digital twin will help us further optimize the as-built data center as we go along, as we maintain and upgrade the facilities. We want to continue the digital twin model of our data center and the machines inside. to be able to do some degree of not just descriptive AI for the operator to tweak and adjust the operations, but also prescriptive and predictive AI. So that's happening right as we speak because our data center is located at the I-4.0 building in the National University of Singapore, which coincidentally also houses AI Singapore's initiative, which is our national AI strategy, the implementer of the national AI strategy of Singapore. This will help us predict what may happen under certain optimization control actions and to understand exactly what's going on in the data center and to determine how we can optimize data center operations using AI techniques. Separately from the hardware possibilities, we also worked with somebody who used our supercomputer to design green data server racks. And we said, wow, you're using our supercomputer to design better racks for cooling systems. What could we make use of your technology? And lo and behold, we are already in the process of engaging them to put in a little bit of Singapore technology into our data center using in-rack cooling systems, using closed-loop refrigerant-based heat removal system and chilled water cooling systems on the water side. This in-rack cooling system will involve some degree of the use of a technology called thermal siphons. And without further ado and belaboring the point, we hope that by putting some intelligence in the system, we could essentially further reduce the overhead of cooling as an energy guzzler. We've engaged an AI company called Red Dot Analytics, a homegrown Singapore startup company, in order to create AI-based what-if analysis and AI-based scenario planning, so that our solution can now be further optimized to eliminate hotspots as well as to optimize PUE of our data center based on IoT sensors that are implanted in our new data center and within our machines and our server nodes. This will hopefully improve on the 6,540 sensors that we already have in Aspire 1. So Aspire 2 going forward will probably have more sensors than the 6,000 IoT sensors that we have right now in our one petaflop system. So preaching what we preach, doing what we, practicing what we preach. We hope also that this approach will ensure that when our urban sustainability project called Cooling Singapore, when they do their survey using satellite mapping and so on, NSCC's Aspire 2 system will not stick up like a sore thumb and it's a hot red spot and a finger pointed at us for being not just a heavy energy user, but also an incredible heat source for dealing with for failing to deal with the cooling problem. So we are highly incentivized to push forward our effort to consider coal energy for LNG regasification for HPC cooling. We have set up a contract and we have linked up with vendors such as such as Keppel Data Centers and Keppel Offshore Marine to couple their capabilities to consider the possibility of using seawater or reservoir water as our heat sink by designing green floating data centers as a possible way of optimizing usage of the land. We can use the water bodies now and provide the cover to reduce water evaporation at the same time. So these are novel techniques that we hope that will eventually pan out if we can do it right. So other possibilities include the use of LNG discharge water for data center cooling and to make sure that we do not pollute seawater with too cold water source from the discharge of an LNG plant that uses seawater to warm the LNG. We could make use of that cold seawater. So the amount of cold seawater is just amazingly amazing because they just dump it into the sea. So there is significant competitive advantage for us to work with Singapore LNG, and we're in the process of negotiating with them. So these options or possibility involving conductive liquid cooling, immersive cooling from LNG plants to using seawater as condenser water, etc. are options that we are evaluating as we speak. So this coal power is a boon to Singapore as a data center hub. If we can figure out a way the supercomputer can be the leading pioneer to drive this project forward, it augurs well for the data center industry in Singapore, because only supercomputing centers have the bandwidth to be able to do all these crazy things and drive all these innovations to tap this kind of potential cold energy source. So in closing, I like to say that we are placing a very heavy emphasis on dealing with this sustainability issue. We're having a bunch of seminar series to deal with this, Future Cool Singapore, and our experts, Professor Gerhard Schmidt and his colleagues, will be talking about Singapore's urban heat island and what steps we are taking to mitigate against this kind of global warming problem. So we hope that if you are available, you can join us at our seminar. And to summarize, supercomputing centers must lead by example. We are already making processes more efficient, but that's not good enough. Could we put data centers in cold places? Could we perform industrial symbiosis with co-locating data centers with other symbiotic systems? Could we make use of warm water direct-to-chip cooling, high-rise? Could we use immersive cooling systems? Can we improve the data center for cooling computer and network devices? Can we put the intelligence into data centers using digital twins, AIs, thermal aware job scheduling, and so forth? Could we optimize our algorithms and so forth and so on? So store less data, think before you compute, improve your algorithms. All these things are ways in which we can work towards HPC data centers of the future, leading by example how data centers of the future could follow. Thank you very much.
Thank you, Dr. Tan.